In this experiment, you'll be using a web-based data analysis tool called iFEED, which stands for Interactive Feature Extraction in Engineering Design. It is a tool that can be used to help analyzing the data in the domain of designing complex systems. In this particular study, you will have an access to the data generated for designing a constellation of satellites. Your task is to interact with iFEED to learn about this data as much as possible. The experiment will consist of two main sessions. In the first session, you will be given 40 minutes to analyze and learn about the data. During this time, you are encouraged to take notes of what you learn. After this 40-minute session has finished, you will be given a problem set to solve. The questions will test how much knowledge you have gained during the learning session. We will first go over the basic structure of the data, and then we will explain how to use the analysis tool to understand it. After this tutorial is finished, a link to the webpage that hosts iFEED will be provided. Please click the link after you're finished with the tutorial. After you have started the experiment, you can come back and refer to the tutorial for more information. The data provided will be in the domain of designing a constellation of satellites to provide operational observations of the Earth's climate. A constellation of satellites is a group of satellites working together to satisfy certain measurement requirements. The data will contain a large number of different satellite system architectures, and each design will have corresponding score and the cost. Different designs will be defined by what measurement instruments are used in each spacecraft and in what orbit each spacecraft fly. Each design can be represented by a figure similar to the one that is being shown. The figure shows which set of instruments are assigned to fly in a particular orbit. Some of the examples of instruments are synthetic aperture radars and spectrometers, but the names have been replaced by alphabets for simplicity. The orbit names have also been simplified as numbers, but they actually represent orbits with different inclination, different altitude, so on and so forth. However, you should not worry about orbits or instruments. Rather, just consider these as different variables and the dependencies between them. In this particular design shown, instruments A, G, L are assigned to orbit 1000, and instruments B, H, K are assigned to orbit 2000. Empty orbit means no spacecraft will fly in that orbit. Instrument E is assigned to orbit 4000, and instruments H, J, and K are assigned to the orbit 5000. Note that the same instruments can be assigned to multiple different orbits. Each design will have corresponding science benefit score and cost. The science benefit score is a score that is computed using very complex models to evaluate the performance and capabilities of each satellite system in measuring Earth's climate. The low cost and high science score design is desired. One thing to note is that particular combinations of instruments and instrument-to-orbit assignments may have synergistic effects. For example, assigning two particular instruments in the same orbit may result in much higher score than having 4 arbitrary instruments in one orbit. Now that you understand how the data structure looks like, we will explain the basic interface of iFEED. When you first follow the link to the page, you will be asked to sign in. It uses Google sign-in system, so you must have a Google account to continue. Since the sign-in is done through Google, the researchers are not able to see your password or any other personal information. This process is done just to ensure that each subject uses this tool only once and only for a given amount of time. After logging in, you will see this interface. And on this interface, you can first see the scatter plot in the middle. The scatter plot displays more than 2000 different designs. Each dot corresponds to one design and is located based on its corresponding cost and the science benefit score. Again, Your goal is to look for recurring patterns that appear among these desirable designs, which should have low cost and high science score. If you hover your mouse over each dot, relevant information about that particular design is displayed on the frame below. First, the science score and the cost is displayed. Then, the design structure of that design is shown below. On the top right, you can check the time remaining. When the time runs out, the page is automatically redirected to a different page and you'll be given the key numbers. The key numbers are to be copied and pasted when you return to the Mechanical Turk. So please make sure that you copy this number and save it somewhere before closing this window. This key number is used to verify that you have successfully finished the 40 minutes of data analysis session. If you quit the experiment before the time runs out, you will not be provided with the key number. On the top left corner, you can see there is a button labeled Enable Drag Selection. When this button is clicked, it becomes highlighted either in green or red color. When it turns green, you can drag on the scatter plot to select a group of designs. Zoom in and zoom out are deactivated while using this function. When the button is highlighted in red color, you can drag to deselect designs. The menus on the right side contain various options you can use to analyze the data. First, you can specify the range of cost and science score, and you can select a group of designs that are located within that range. After that, you can cancel the selection by clicking the Cancel All Selections button. And after selecting a group of designs, you can also click Hide Selections button to hide them. By hiding designs, you're excluding them in other calculations in the analysis process. You can click the Next button to make all hidden designs visible again. The threshold setup options are options that you can control in extracting driving features. Explanations about driving features and classification tree will be provided later. The button that is on the bottom is used to open filter options. Filters can be used to select a group of designs that share the common pattern or feature. For example, you can selectively highlight designs that use instrument C or designs that assign instrument D and E to orbit 4000. Such selective highlighting function is useful to see how designs that share the same pattern are distributed in the scatter plot. You can select one of the preset filters to specify what patterns you want to investigate. The first preset filter that you can use is Pareto front. Here, you can put in an integer number as an argument. And if you click Apply New Filter button, then the corresponding designs will be highlighted on the scatter plot. A design being on the Pareto front means that the given design is better than or equal to all other designs in all objectives and strictly better than in at least one objective. You can imagine that if you remove these designs, you will have another layer of Pareto front. The Pareto ranking is related to the number of layers that you need to remove for each design to be included in the Pareto front. A filter called present can take in one instrument name as an argument, and it means that that particular instrument is used in any orbit in a given design. For example, if you put in instrument A as an argument, then all the highlighted designs will contain instrument A. Absent also takes in one instrument name as an argument, and it means that that particular instrument is not used in a given design. In orbit takes in one orbit name and one instrument name as arguments. This indicates that the specified instrument is assigned to the given orbit. Not in orbit is the exact opposite of in orbit. This means the specified instrument is not assigned to the given orbit. Together takes in 2 or 3 instrument names as arguments. You should use commas to separate instrument names. This would mean that those instruments are assigned to the same orbit. Together in orbit is similar to the previous one, but here you can also specify the orbit name. Then all the given instruments are assigned to that orbit. Separate takes in 2 or 3 instrument names separated by commas, and this means that those instruments are not assigned to the same orbit. Empty orbit takes in 1 orbit name, and it means that particular orbit will have no instrument assigned to it. Num_orbit used takes in an integer number between 0 and 5, and it indicates the number of orbits that are not empty. Subset of instruments takes in multiple arguments. First, you can specify an orbit name, then a number or 2 numbers separated by a comma. Then you can specify a set of instrument names. For example, let's assume that you put in 1000 as orbit name, 2 and 4 for the second field of arguments, and instrument names A, B, C, D, E, F, G, all separated by commas. This will highlight all the designs that have at least 2 and at maximum 4 number of instruments out of A, B, C, D, E, F, G assigned to the orbit 1000. You can also define a new filter setting from Define New Filter menu. The new filter can be defined as a logical combination of preset filters, and therefore you can make more sophisticated filters that better separates desirable designs from the rest of the designs. In order to use it, you first have to select the preset filter that already exists. Then, you can type in the arguments such as instrument or orbit names. Then click Add this feature button. When you want to add more filters, just select another one and again put in appropriate arguments. But before you click Add this feature button, make sure you first click the logical connectives between filters. Then if you click Apply Filter, it will act like any other filters. If you specify the name of this newly created filter, you can save it for analysis at later stages. Now, if we go back to the main interface, there was a button called Get Driving Features. Driving features are the patterns that appear more often among the selected group of designs compared to all other designs. Extracting these patterns can be useful to learn what constitutes good designs. So when you click Get Driving Features button, it will run a data mining algorithm to extract these patterns. But before you click this button, you first need to select a group of designs that you want to investigate. Selecting the target designs can be done in 2 ways. You can either use the Enable Drag Selection button, which can be found on the top left corner, or you can select the range of values for cost and design score using the menus on the top right. After selecting the group of designs, you can click the Get Driving Features button to extract driving features. Then the driving features are presented as bar graphs. Different colors of the bar represents different preset features. If you hover over each bar, the name of the driving feature will appear. Below the names are the metrics that shows how useful, interesting, or statistically meaningful each driving feature is. Also, as you hover over each bar, the designs that contain that particular driving feature are highlighted on the scatter plot in pink. The 3 metrics that are used to infer the usefulness or interestingness of each driving feature are support, confidence, and lift. Larger is better for all 3 metrics. More detailed explanation can be found in the Mechanical Turk directions. The last tool that can be used for analysis is classification tree. Classification tree is a decision tree that classifies whether a design belongs to a target region or not. Similar to driving features, you have to select a group of designs before you can build classification tree. When you click the Build Classification Tree button, a new window will pop up and the tree graph will be displayed. Each of the test nodes of the tree corresponds to a driving feature. All the designs will start from the root node, which is on the far left, and will follow the branches depending on whether it contains the driving feature specified at each node. If a design contains the driving feature, it will follow the green line. Otherwise, it will follow the red line. Each leaf node, which are on the far right, can be expanded by clicking on the node. When it is expanded, it becomes a test node and the tree size will grow. The information displayed at each leaf node indicates whether the designs that reach the node are classified as selected or not selected in the GUI. The classification accuracy is displayed inside the parentheses. The weight indicates the number of designs that reached the leaf node. Now the tutorial is finished. You will be given 40 minutes after you log into the system. You are encouraged to take notes while you analyze the given data. After 40 minutes have passed, the page will automatically redirect it to a different page that contains a key number and a link to the survey. You should copy and save the key number, as you will need to provide it in the survey for verification purposes. In the survey page, you'll be asked a set of problems to test your knowledge on the dataset. Some sample problems is provided in the Mechanical Turk. The actual questions will be similar to the sample problems, but not necessarily the same.